Good morning, folks.
Good morning.
Good morning.
Good morning, everyone. Just waiting a moment to get everybody logged in here. Okay. All right, I think we'll get started. So welcome back and good morning. I hope you had a nice weekend. We're moving into my favorite time of the year as we approach the fall. So, when you get a chance to be outside, I encourage you to take advantage of it. Okay. Folks, we're going to continue our conversation in chapter 2. We had just started talking a little bit around the border of what an ionic bond is, and we need to continue that conversation and extend off of it today. Okay, so before I do that, do you have any questions at this moment? Okay, all right, well, welcome back. Let's get started here. I want to share my screen with you. And get my desktop set up so that we can take some notes. Okay. So what I've done here is create a new document, and I've placed the last notes from our conversation last class. I always have up here from last time, right? So we were talking about chemical bond definitions, and we just got started talking about an ionic bond. As you know, an ionic bond is an attraction created between atoms when one atom donates one or more electrons to a neighboring atom. So at this point, what we're going to go through is the example of sodium chloride being a molecule that the two atoms that are joined together are joined by an ionic bond. And I want to start to give you a feel and intuition and understanding for why these two atoms would be attracted to each other. Okay, I encourage you to please have your textbooks up on your computer at this time, because I will be asking some questions where I need you to refer to information in your textbook. Okay, so on the screen, we have sodium and chlorine drawn out here. And again, I have intentionally separated them from each other so that they appear that at the moment, they're not really connected to each other because I've drawn them far apart. All right, so let's continue the conversation. And so I want to refer you to, okay, we're going to be flipping back and forth between figure 2.2 on page 32 and figure 2.4 on page 34, right? Those are your reference pages for the moment. Okay, let's continue here, and let me just see if I can get someone to help me out with this today. Okay, so let's see. Is Brittany Singer online with us today? Brittany, can you say hi to us?
Hello.
Morning, Brittany. Brittany, do you have your book available?
Yep.
Great. Okay, so Brittany, on page 32, I'd like you to answer a few questions for me if you can. And this is to help everybody, so everybody should be thinking about this. Brittany, on page 32, can you tell me how many protons are in the nucleus of a sodium atom?
1 second. How many protons are in a nucleus of a sodium atom?
Correct.
Alrighty, 1 second. Is it 11?
It is 11, right? So what piece of information did you read off of page 32 to answer that?
I used the figure 2.2 and I looked at the sodium cell
Okay, you looked
and I
at,
used the atomic number.
okay, very good. You looked at the sodium atom and used the atomic number equal to 11. Very good. Okay, so Brittany, stay with me. So I'm going to draw on the screen.
Okay.
I'm going to draw on the screen that I have 11 protons here. So 11 with a little plus sign for a positive charge. So Brittany, one of the things that we haven't necessarily told anybody yet, but you may or may not know, is that when we talk about atoms as they're listed on the periodic table of elements, atoms are assumed to be electrically neutral. Okay, that's our starting point for thinking.
Okay.
So atoms are assumed to be electrically neutral. Okay, so Brittany,
Yes.
if sodium has 11 protons, how many electrons would it need to be electrically neutral?
One second.
Once
Would it be
again,
12?
okay, why do you say 12?
Because it says 12N on the atom, and I was thinking that means neutral. I don't know.
Oh,
And I did 23 minus 11.
okay. Well, tell you what, that 12N is referring to neutrons, not
Okay.
electrons. So do you want to revise your answer?
Can you ask it again?
Okay, so if atoms are supposed to be electrically neutral,
Okay.
and sodium has 11 positively charged protons, how many electrons would it need to be electrically neutral?
All right. Honestly, I don't know. Maybe 5.5. Divide the 11.
Okay, thanks, Brittany. I appreciate your participation today. I really do. Let me see if we can help you along. So
Thank you.
if we have 11 positively charged protons, doesn't it make sense that we would need 11 negatively charged electrons to counterbalance that? If we had a seesaw,
yeah.
if we had a seesaw and I had 11 people on one side of the seesaw, I might need to have 11 people on the other side of the seesaw to balance it out. So, in fact, we will have 11 electrons here. Okay.
Okay. Yeah, makes sense.
Okay. Thanks, Brittany. All right. So I'm going to just continue with this line of reasoning and ask everybody to follow along. If we continue by looking at the information on page 32, we'll notice that the chlorine atom has an atomic number of 17. So that means I have 17 protons here. And to be electrically neutral, I'm going to need 17 electrons. Okay. So I have two electrically neutral atoms. This is our starting point for chemical theory. Okay, that the atoms are electrically neutral. So the number of protons and electrons are assumed to be the same. Now let's think about this for a moment. If every atom, the two atoms in front of you, sodium and chlorine, or any two atoms on the periodic table, are electrically neutral and they remain electrically neutral forever, then there would be no reason that they would be attracted to each other. Again, if atoms maintain their neutrality, there's no reason that they would be attracted to each other. And if that were the case, atoms would never join together to build molecules. And if that was the case, you and I would not be sitting here this morning having this conversation because we would not exist. Okay. So something has to disrupt that neutrality. All right, so here's where things get a little crazy. All right, and let me just talk in some generic language at this time. Atoms like sodium and chlorine you have on your screen, or any atom of the periodic table of elements, any atom on page 32, any atom of any kind. Atoms are kind of like human beings. And what I mean by that is every person on the planet has his or her unique personality. Some Some people have a dry, sarcastic sense of humor. Some people have a very lighthearted, bubbly sense of humor. We're all different people with different personalities. Some of you like to drive a certain car. Some of you like to drive a certain truck. Okay. Some of you like to eat a certain food. Other people like to eat different food. Some people like to eat meat. Other people like to eat plant material. They're vegetarian, right? We are different people with different personalities. Well, the atoms of the periodic table have their unique personalities too. Now, they don't literally have a personality like a human, but they have characteristics which are unique to them. Okay. And so this is where we go and we turn to page 34, figure 2.4. Page 34, figure 2.4. Okay. If you look at figure 2.4 and you look at panel A of figure 2.4, you'll notice the green sodium atom. And you notice in the upper left corner, your book, the upper left corner of figure 2.4, the upper left corner of figure 2.4, do you notice your book is showing you that the outer green ring of electrons has a single electron, one electron. Well, as it turns out from observations that chemists have made over the years, that that outer electron ring really should have it really should have 8 electrons if that atom is going to be a stable atom. And by stable, I mean it's content to not interact with other things. But as it were, sodium only has 1 electron in that outermost green ring. So let me ask this in the chat window. Let's get everybody answering here. How many rings of electrons are shown around the sodium nucleus? How many rings of electrons are shown around the sodium nucleus in figure 2.4? Okay. So even if you don't know the answer, I'd like you to look at the chat window and notice that pretty much everybody's saying 3, and that's exactly right? There are 3 green rings of electrons around the sodium nucleus. Okay, the outermost or thirdmost green ring has a single electron when it really should have 8 for the atom to be stable. Since it only has 1, we can think of the sodium atom of having a personality where it is irritated or unstable. Okay, and so what happens here is for sodium to become a more stable atom, sodium has the option of either acquiring 7 electrons from some other source in the environment to fill up that third outer ring, or alternatively, simply getting rid of 1 electron and destroying that outer third ring of electrons to only have 2 rings of electrons. Okay, so let me ask you something pragmatically in the chat window. Let me get my wording here. And here we go. If you could make yourself more happy by acquiring 7 items you do not have, or getting rid of 1 item you do have, which path to happiness would be easier? Think about it from your own personal perspective. If you could make yourself happy by getting 7 things that you don't currently have, or getting rid of 1 thing you do currently have, which is just pragmatically easier, okay? I think most of us can come to the conclusion as well, if I already have 1 item that if I just get rid of it, then I'm going to be a lot happier than trying to get 7 things from some location I don't have. That's the easier path. So that is what sodium will do. You will see it in your own textbook, figure 2.4, where it says there, electron donated. Okay, and it's showing you a red colored electron. Obviously, electrons don't have a color, but they're color coding it for you in the book so you can understand what's happening here. So what I'm telling you is that sodium has a personality where it tends to get rid of an electron in order to become stable. So I'm going to draw it on your screen for you like this. Okay, so sodium will eject one electron. Okay, all right. So let's see here. Kathy Dozier. Kathy, could you please say hi to us?
Hello.
Good morning, Kathy.
Morning.
Kathy, got a question for you, and just can you see my screen okay?
Yes, I can.
Okay, so Kathy, let's follow the logic here of what we're talking about. If sodium has ejected an electron, how many electrons are left around the sodium atom?
Um,
So let me just ask it a different way. Kathy, if sodium gets rid of one electron, how many electrons would remain?
I don't know.
Look at the information on the screen in front of you, Kathy. Okay, so how many electrons did we say is around sodium when it was neutral?
11.
Okay, good. So if it started with 11 and it got rid of one, how many would be left?
Oh, 10.
Okay, that makes sense, doesn't it?
Mm-hmm.
Okay, so now stay with me, Kathy. So Kathy, if I now have 11 protons around the, if I have 11 protons in sodium and only 10 electrons, is there an imbalance? Is there a scenario where I have more protons than electrons?
Um, yes.
Okay, so how many more protons do I have than electrons, Kathy?
7.
No, I have 11 protons right now and I have 10 electrons. So
Oh,
how many?
1.
Okay, I have one. So what I'm telling you, Kathy, is when sodium gives away when sodium gives away one electron, we
Mhm.
have an imbalance of one proton, which means the overall charge on the sodium atom becomes +1. Does that make sense, Kathy?
Yes.
Okay, stay with me then. So let's continue our conversation. So Kathy, if chlorine has the personality that it would like to accept the electron that sodium gave away, and let's say that chlorine does that. Chlorine accepts the one electron that sodium donated. How many electrons will be around the chlorine atom?
18.
18, nicely done. So Kathy, if I have 18 electrons and 17 protons around the chlorine atom, how many more electrons do I have than protons? Kathy, what do you think? If I have 18 electrons and 17 protons, how many additional electrons do I have than protons?
1.
1. And because an electron has a negative charge, the overall charge on the chlorine atom becomes -1. Okay. Thanks, Kathy. Appreciate your help today. Okay.
Mm-hmm.
All right, folks. So what I'm trying to get to is the punchline here. Okay. When sodium and chlorine donate and accept electrons, they take on excess charge, which means that the sodium and chlorine atoms become sodium and chlorine ions. Okay. When neutral atoms eject or accept electrons, the atoms become ions, right? The ions are electrically charged atoms. Ions are electrically charged atoms. Right now in our example, sodium has a +1 electric charge. Chlorine has a -1 electric charge. Okay, so what I'm trying to get you to see is that these atoms take on different charges. And what we would do is go back to that old statement you learned since you were in elementary school, that opposite charges attract each other. So these two atoms are drawn towards each other because they are now attracted. You might ask yourself a very reasonable question, why does it work that way? And while that is a good question, I think it's probably only a question that God could answer, because we don't know why the universe was constructed to be the way it is. We can simply observe what happens and describe it, okay? But I can't tell you why it happens that way. Okay, so long story short, when sodium gives away an electron, it becomes a positive ion, a positive sodium ion. When chlorine accepts the electron, it becomes a negative chlorine ion. These two ions have opposite charges. Opposite charges are attracted to each other for reasons we don't necessarily fully understand, but this opposite charge effect creates the actual ionic bond, which is the whole purpose of our conversation here this morning, talking about ionic bonds. Okay, folks, do you have questions?
Nope.
Okay, let me ask you all a question in the chat window. Okay. Are you with me? Is this logic making sense? Can you see where I got the numbers from? Do you understand how sodium went from 11 electrons to 10 electrons and so on and so forth? Okay. All right, so you let me know, please let me know if you have questions. Okay. All right, let's continue. All right, so let me see what I can do here. The next thing we need to do is talk about covalent bonds. Let's see, that should be letter B here. Okay, so covalent bonds are shown to you in various examples of covalent bonds, single bonds, double bonds, triple bonds on page 36, figure 2.5. If we have single bonds, we have one pair of shared electrons. If we have double bonds, we have two pairs shared electrons. If we have triple bonds, we have three pairs of shared electrons, okay? So I think that's pretty simple, but let me give you a definition here. Covalent bonds are attractions created between atoms when atoms share electrons. So the key language for an ionic bond is one atom donates or gives away the electron. Whereas with a covalent bond, we are sharing the electrons. So think about transferring or donating bonds, transferring or donating electrons for the ionic bond scenario versus sharing electrons for the covalent bond scenario. Now, there's two important types of covalent bonds that I want to talk to you about today, and that would be nonpolar versus polar covalent bonds. Nonpolar versus polar. And here I need to do a little bit more drawing for us. Okay, so please bear with me here. And so I'm going to just divide our workspace into two areas here. Let's do the nonpolar situation first. When you have a nonpolar covalent bond, what that means is that the electrons are evenly or equally shared. Electrons are equally shared. Well, please understand what I mean by that, okay? If you were going to share a pizza with your friend, you could cut the pizza in half and give your friend half the pizza and you would keep half the pizza for yourself. That is not what is taking place here. Because an electron is not a pizza, we can't cut the electron in half. But what we can do is share the time of the electron and where the electron spends most of its time. In other words, if you think about it for yourself, you have 24 hours in one day, right? You can only be at one place so long, right? So you might be at your workplace for 8 hours a day, and you might be at home for another 8 hours a day while you're sleeping, and you might be at the shopping mall for another 8 hours a day, right? That's 24 hours. But if you're at work for 8 hours and you're at home for 8 hours, that means you are sharing your available time with your work and your home life equally, okay? So we're not cutting the electron in half. When I say we're sharing electrons, we're sharing the electrons' time, okay? And so an example of this would be a carbon-carbon bond, where that line between the two carbon atoms is a symbolic representation of a bond. But if I were to draw this a little bit differently, I might try to make an attempt to show you how the motion of electrons is shared. Okay, so I'm not really a good artist, but let me just make an attempt at this. I'm going to draw a dotted red line on the screen, and I'm going to try to outline the motion of the shared electrons. Here we go. Okay, so again, I'm not a good artist, but what I'm trying to get you to see is that roughly 50% of the time, the electrons being shared are orbiting the left carbon atom. And the other 50% of time, the electrons being shared are orbiting the right carbon atom. And if I was a perfect artist, I would have drawn the dotted red line of an equal shape and volume around the left and right carbon atoms. Okay, so this is what I mean by sharing electrons equally. Key to understanding this is a very simple observation. Do you notice that the carbon-carbon bond is nonpolar? And you might ask yourself, well, why is it nonpolar? For a first approximation, it's nonpolar because both atoms participating in the bond are the same type of atom. Carbon and carbon, nitrogen and nitrogen, sulfur and sulfur. It's like having a tug of war with a clone of yourself. If you had a tug of war with yourself, okay, that would be a pretty equal matchup, would it not? Because you're competing against yourself. Okay, so notice that both atoms are the same. Okay, folks, do you have any questions about non-polar covalent bonds? Okay, let's continue. I will transition to the polar covalent bond description. For polar covalent bonds, well, obviously there's going to be something different from what we just described. For polar covalent bonds, the electrons are unequally shared or unevenly shared, okay? So I'll just say it this way, it's an uneven sharing of electrons. A good example of this would be a hydrogen-oxygen bond, okay? And so let me do the same thing where I try to draw out the motion of the electrons that are being shared, okay? And if I were to do that, what I'm hoping you will notice as the electrons being shared create a shape that is very imbalanced, not equal. So they would kind of look like this. Okay, where you see the volume of space outlined around the right oxygen atom is much larger than the volume of space outlined around the left hydrogen atom. That's because there's an uneven sharing of electrons. That means of the electrons being shared, maybe 10% of their time is spent around the hydrogen atom, but maybe 90% of their time is spent around the oxygen atom. Okay, and you notice in this kind of bond, notice that both atoms that are participating in the bond are in fact not the same. Okay, the atoms are different. Okay. Now, in both cases, whether it's a nonpolar or polar covalent bond, the electrons are being shared either equally or unequally. So again, if I go back to a tug of war analogy where you're having a tug of war either with yourself or simply your friend, you know, what is the competition for? What is the tug of war competition for? It's for the shared electrons. How much the electrons are going to spend around you versus around your friend, okay? So the competition is for the shared electrons time. The competition is for the shared electrons time, okay? So I want to give you an idea of how you can predict whether a bond will be polar or nonpolar. First off, these statements down here are both good statements. You know, nonpolar, both atoms are the same. Polar, the atoms are different. That goes a long way to predicting whether the bond will be polar or nonpolar. But we can go a little bit further, a little bit deeper into chemical theory so that you appreciate this. Okay, you might ask yourself, in this polar example, why do the shared electrons spend more of their time around oxygen? So let's make that a question, okay? Question. Why do the shared electrons spend more time around oxygen? Would anybody like to offer an answer to that question?
Is it because it has a bigger mass?
Noah, because you say it has a bigger mass. That's an interesting question there. That's not what chemical theory would suggest, although I can't deny that larger mass of objects often have a stronger gravitational pull to them. So I think that was a very reasonable statement, and I think in reality that probably has a little bit to do with it. So that was a very nice statement, Noah. That's not what we would typically say from a chemist perspective, but I really did like what you said there. Okay. Okay, so let's see here. Hold on a sec. Raquel, I see your hand up. Just a sec. Brianna, in the chat window, you say it has more electron shells, causing it to have more electrons. Brianna, you might be onto something there, but you kind of explained it backwards. So hold on to that thought. Raquel, do you have a question?
It's more electronegative, so it's more like electrons will be more attracted to it.
Okay, so Raquel, you say it's more electronegative. Well, why would one atom be more electronegative than another atom?
Well, in my other chemistry class, I learned about how like the nucleus, size kind of has an impact on it, but depending on like the size of the nucleus, it'll pull electrons towards it at different like rates, I guess. And oxygen is one of the most electronegative, so it pulls more electrons towards it.
Raquel, I agree with you. And I agree a little bit with Brianna, and I like Noah's answer. But Raquel, that was a good statement. But we want to get down to the goodies here. So again, what you're saying is not false. what you're saying is very true and reasonable. I just want you to go deeper. Why is it that electrons should be more attracted to the oxygen atom? I want you to all see that there is a very reasonable, simplistic answer here. Raquel, you used the fancy word electronegativity. And by the way, I would like everyone to definitely study what that word means. So I'm going to type it into the chat window. Electronegative, that's something that you should be thinking about. But okay, let me draw us to a conclusion here. And let me just ask everyone to follow along here. Page 32, figure 2.2. I will ask it. Well, let me ask the questions in the chat window. Okay, so here we go. First question. How many protons are in the nucleus of an oxygen atom? How many protons are in the nucleus of an oxygen atom? Good job, folks. Love that it's coming through here. Take a look, everybody. If you don't know the answer is in fact 8. And ask yourself, well, where did they get 8? Everybody got 8 by reading the atomic number, correct? So now, hopefully you can see where I'm headed with this. Let me ask the next question. Here we go. How many protons in the nucleus of a hydrogen atom? Yeah, it's just 1, right? So let's think about it this way. If we have a tug of war for electrons, tug of war for shared electrons, and I have team oxygen with 8 positively charged particles, team oxygen with 8 positively charged protons versus team hydrogen with 1 positively charged proton, doesn't it make sense that oxygen should be better at pulling electrons towards itself because it's got a larger team with more positive charge, which is basically the answer to your statement, Raquel. What makes an atom more electronegative than another atom? Well, it goes a long way to talk about the number of protons that are present in its nucleus. Okay, so let me write this down. So we've got the answer in our notes. Okay. All right. Why do the shared electrons spend more time around oxygen? And the answer is because the atomic number of oxygen is 8, and the atomic number of hydrogen is 1. Again, think about a tug of war for electrons. Team oxygen, 8 team members, 8 protons. Team hydrogen, 1 proton on its side. Okay, so question in the chat window. Are you okay? Is this making sense? Would you like to ask any questions? You know, there's an old quote that's often attributed to Albert Einstein. And honestly, I don't know if he really said this or not, but people say that he said it. And basically, it's something like this, you know, if you're talking about a complicated topic in science or engineering or any of the, you know, thing like that, technical information, if you cannot explain it to grandma, then you probably don't understand it yourself. And that's not to disparage grandma. Grandma might be a theoretical physicist and grandma might be brilliant. But you know how it is, right? If you can explain something technical to grandma, then you probably understand it very well. Okay, and that's what I'm asking you to do when you do your study time. Okay, don't be satisfied with an answer that you kind of get, but you don't really get. Don't be satisfied with, okay, I can spit out some fancy words that might give me credit on an exam, but I don't really understand this yet, okay? You want to dig down for as true an understanding as you can get away with. And that process, honestly, will never stop the rest of your life, because we are all students the rest of our life, right? Our knowledge, understanding is continually maturing, changing, updating itself, okay? Do you have any questions? Okay, gang, let's continue here. All right, so this sets the stage for our next conversation. Hope I can do this. Let's see here. For our next conversation, which will be hydrogen bonds. Okay. Now, hydrogen bonds are described to us. There's some language about hydrogen bonds on the bottom of page 35, and there's some schematics and drawing of a hydrogen bond and so forth on page 37. So let me give you an English definition, then we'll talk about this. Hydrogen bond is an attraction between a slightly positively charged hydrogen atom and a slightly negatively charged atom, which is often, but not always, it is often oxygen nearby. Okay, let me say it one more time. Hydrogen bond is an attraction between a slightly positively charged hydrogen atom and a slightly negatively charged atom, which is often oxygen nearby. So I'm going to see if I can take our previous conversation and get you to connect the dots, right? I mean, we just celebrated the hallmark of September 11th this past weekend, right? 9/11. And I know for some of you that some of you may not even been alive during 9/11. But some of us lived through it. I certainly lived through it. I remember it. And, you know, long story short, what was one of the criticisms of our government that people had? Well, after 9/11, one of the criticisms was that why didn't the government catch these terrorists before these bad things happened? And the answer basically is because the government was not able to connect the dots with information they had. They were not able to connect the dots. Now, let's be honest, the government is people. People are flawed. Nobody's perfect. That's how it is. But the basic criticism has always been, well, people working in law enforcement at the national level did not connect the dots, and that's what allowed this to happen. Whether you believe that or not, that's the issue. Can we connect the dots with ideas and concepts? Do we see the relatedness between seemingly different things? Here we go. All right. So with a hydrogen bond, let me start with this drawing here. I'm going to draw a water molecule. Okay, so here we go. H2O. This is one water molecule. Okay, and let me just take a quick look here at who I've got online. Okay, all right, okay. Is Morgan Bruni online today? Morgan, can you say hi? Okay, all right. So let's see here. Let's see here. Is Madison Coulter online? Is Madison with us?
Hi, I'm here. Sorry.
Hi, Madison. I can just barely hear you. Are you able to speak up a little?
Sorry, my voice is like gone. Can you hear me?
I can hear you. Okay. Good morning, Madison. Madison, with the water molecule that's drawn on the screen, can you tell me how many hydrogen bonds are present?
Isn't it 2?
Okay. All right. Thank you, Madison. I appreciate your participation today, and I hope your voice gets stronger, that you feel better that way. So Madison
Thank
said
you.
that there's 2 hydrogen bonds on the screen, and I'm just going to ask everybody in the chat window. Do you agree that there are 2 hydrogen bonds drawn on the screen? Remember, folks, it's all about participation. You don't have to be perfect. You don't have to get everything right. I just want you to participate. Okay. And so thank you for those that are continuing to offer their responses up, right? So let's just be clear here, right? So right now, here's the bonds we're talking about, right? I'm putting them in a blue rectangle, right? Okay. Yeah, so the answer to my question is 0. There are 0 hydrogen bonds drawn on the screen right now. Okay, the answer is 0. It's not 2. Wait a second, what the heck's going on here? Okay, folks, those bonds that I've just highlighted in blue, they are not hydrogen bonds. What kind of bonds are these? Type into the chat window what kind of bonds these are. What kind of bonds are highlighted in the blue rectangle? What kind of bond are they? Okay, so all of you are starting to say covalent. Good. So tell me now, are they polar or nonpolar? Are they polar or nonpolar covalent? Okay, good. They're polar. That's right. These are polar covalent bonds. Polar covalent bonds. Good, folks. Awesome. Do you see, excuse me, I've got to move the screen on you. Do you see the relatedness between our previous conversation with hydrogen and oxygen, hydrogen and oxygen, hydrogen and oxygen, and the hydrogen and oxygen that are present within one water molecule, right? Those bonds are in fact polar covalent. So at the moment, there are no hydrogen bonds drawn on the screen. There are none at the moment. We're going to change that next. Here we go. So I'm going to draw a second water molecule. Here we go. H2O. Here's the second water molecule. These bonds are also polar covalent. Okay. Any questions you'd like to ask before I continue? Great. Okay. So gang, I'm going to move back up a little bit to our hydrogen oxygen example here. Folks, this HO bond that we spent a lot of time talking about, one thing I didn't mention to you, but now I do have to mention to you, is the following. If there's an imbalance in how the electrons being shared between these atoms, if that imbalance exists, then it makes sense, does it not, that the oxygen atom, which has the electron 90% of the time, is going to have a little bit of excess negative charge because the electrons being shared spend most of their time around that atom. So I'm going to get this weird thing. Okay, when you see this weird symbol, this is a Greek symbol which means partial. So I'm saying to you that oxygen has a partial negative charge because that atom has the electrons most of the time, 90% of the time. The hydrogen If the oxygen has the electrons 90% of the time, that means the hydrogen does not have the electron 90% of the time, which means 90% of the time, the hydrogen is deficient in electric charge and negative charge. So hydrogen takes on a partial positive charge. Okay. All right. Taking this information and moving it down to our water conversation. Right, we know that the electrons are being shared unequally here, so that means I take on a partial negative charge around oxygen, partial positive around both hydrogens. Same thing's going to happen on both water molecules, partial negative around oxygen, partial positive around hydrogen. And what I'm wanting you to see is that, in fact, I have set up a situation where I have a partial negative here with a partial positive sitting next to each other. In other words, I have slightly oppositely charged atoms sitting next to each other. And you know that if I have opposite charges, there's going to be an attraction formed. So in other words, this is going to be the hydrogen bond. Okay. This is going to be the hydrogen bond. What I'm emphasizing is that the hydrogen bond, let me turn that off, the hydrogen bond is often, but not always, formed between atoms that are part of different molecules. Often, but not always, formed between atoms that are part of different molecules. Look at the drawing. The top oxygen is part of the top water molecule. The bottom hydrogen of the hydrogen bond is part of the bottom water molecule. Those two atoms are part of different water molecules. So the hydrogen bond frequently forms between atoms of two different molecules. Okay. All right. So at the risk of not wanting to go too deep and making the understanding even worse than it might already be, let me ask you, do you have questions?
Could you give an example of a hydrogen bond within one molecule?
Okay, I'll give it to you verbally, but I'm not going to draw it or write it out. Okay, it is possible in very large molecules, like large proteins such as insulin or DNA, that you could have an oxygen atom on one end of the molecule and a hydrogen atom on the other end of the molecule, that when the molecule kind of bends and twists around, that those two atoms get close together to each other, and then you could have a hydrogen bond between the oxygen and hydrogen within the same large molecule. That can exist as well.
All right, thank you.
Okay, other questions? Okay, I have a question for you in the chat window. I'm going to make a statement, and I want you to tell me if it's true or false. Hold on a second. Let me get my language correct here. Okay, this is good enough. True or false? Hydrogen bonds cannot form if the atoms within each water molecule were connected by nonpolar covalent bonds. Is that true or false? Okay, thank you for your responses, everybody. And let me say that perhaps I've done a poor job, because the answer to that is true. Okay, let's go back up to the statement. True or false? Hydrogen bonds cannot form if the atoms within each water molecule were connected by non-polar covalent bonds. Here's what I'm trying to get at up here. Let's see here. Hold on a second. Okay. Yes. Okay. Okay. Folks, if these bonds that are in blue rectangles were in fact non-polar, if they were non-polar, that means there would be an equal sharing of electrons, an equal sharing of electrons. If there were an equal sharing of electrons, then the oxygen and hydrogens would not take on partial charges. Oxygen would not have a partial negative. Hydrogen would not have a partial positive. They would be basically neutral. So if these bonds in blue were non-polar, you would not create partial charges. And if you don't create partial charges, then there's no reason for the oxygen and hydrogens of two water molecules to be attracted to each other. Let me ask you a question. Chat window. Did my explanation just make sense? Do I need to say it again? Do I need to type it out in your notes? Okay, Brittany, I appreciate the response. How about all of you? Okay, all right. Okay, so I'm going to take my language from the chat window and put it in your notes. Okay. And let's see here. Yep. All right, true or false? Okay. True or false? Hydrogen bonds cannot form if the atoms within each water molecule were connected by non-polar covalent bonds. That is, in fact, true. Non-polar covalent bonds would mean that oxygen and hydrogen atoms within each water molecule would not take on a partial charge. They would not take on a partial charge, positive or negative. Therefore, there would be no basis for attraction between the oxygen of one water molecule and the hydrogen of another. Let me take a look at the chat window here. Okay. All right, so folks, as you think about what I've just written on the screen, and maybe you're writing it down for yourself, is the explanation making sense to you? How can I help you at this time? Is there anything you'd like to ask about hydrogen bonds before we move on? Okay, folks, I'm going to move on. Sometimes you gotta wrestle with content. You got to think about it for a while on your own before you realize whether you understand it or you don't. And I want to encourage you to do that. And if after spending some private time with the content, you're like, I still don't get this, then that means either you need to ask me a question, you need to come to my office hours, you need to go get a tutor, you need to ask another classmate who says they do understand it, but you don't want to stay silent about it. You want to get help, okay? All right. Okay, gang, so congratulations, you have now made it through the chemical bond torture chamber here in AMP1. Okay, so we're done with chemical bonds, but we're not done with the chemistry chapter. Okay. What I want to do now is talk to you about water. And the reason I'm going to talk to you about water now is because we just got done talking about hydrogen bonds in the context of two water molecules. So it seems like a good springboard, a good transition into the topic of water, and that's what I want to do. So I'm going to move to page 40 in your textbook, where it talks to you about inorganic compounds and solutions, and it talks about water. Okay, water is extremely important to life. And so, you know, I would be remiss if I didn't at least mention water to you. So the next major heading of our notes is the important biological properties of water. Okay. We know, I think we know from previous statements, that basically 65 to 70% of your body mass is water. That means, roughly speaking, if you were 100 pounds and you stepped on your bathroom scale, 65 to 70 of those pounds would in fact be simply due to the presence of water molecules in your body. We are basically big sacks of water with two eyeballs. We are more water than we are anything else. Okay. Water makes life possible. Okay. So number one, chemical reactions inside your body take place in the presence of water. Okay, so let's see here. I see your message, Kelly. Thank you. I have a question for you in the chat window. I really would like just a very honest answer from you, okay? There's no correct answer. It's just tell me what you honestly think here. So here's my question. Here we go. This morning, have you given any conscious thought to the air in the room you're sitting in? Have you thought about the air in the room you're sitting in? Okay, so go ahead and take a look at everybody's answer. Seems to me that the majority is probably no. There might be some yeses, and that's fine, because let's be honest with you, you might have thought about the air because the air in your room might have been chilly, right? Because it's a cold morning, so you might thought, oh, it's kind of chilly. Or maybe the air in your house is very humid. You say, oh, well, it's very humid. Or maybe it's, overly dry. It's very dry air. It's possible you thought about the air in the room, but as you look at the answers in the chat window, it seems that most of you did not think about the air in the room. And that's my point. The point is that most of us spend most of our time not ever thinking about the air around us. We take it for granted it's there, and we just go out of business of our daily lives, paying bills, getting groceries, taking care of the children, watching a television show, whatever it might be. We take it for granted. And that's the point. It's there, and it's mega, mega super important, but we take it for granted and don't think about it. The same thing is true of water. Water is in the cells. Water is there when the cells are performing chemical reactions. And a lot of times we humans and scientists take it for granted and don't even consider it. But the point of it is this: not only are chemical reactions taking place in the cells of your body in the presence of water, it is the water that allows the chemical reactions to happen properly. Water allows the chemical reactions to happen properly. So I'll say it very bluntly. Okay. The chemistry of life requires water. The chemistry of life requires water. And if water were not present, life would not occur. Okay, so water is super, super mega important, although we often ignore it. I mean, think about it practically speaking. You know, let me ask a question in the chat window. Do you know anyone that was ever hospitalized due to dehydration? Okay, I can hold up multiple hands because that's happened in my family a couple times, right? I was like, what the hell's going on here? Why are you in the hospital? Oh, you're dehydrated. Okay, it happens. It's easy to happen, particularly as we get older. As people get older, it's more likely that you will be dehydrated. So we could talk about that at another time. But my point is that if you don't have the proper water content in your body doesn't function properly. Why not? Because the proper water isn't there to support the chemistry. You get sick, okay? So water is super important for the chemical reactions of your body. That's number one. Number two, water is the universal solvent. Water is the universal solvent of the body. And, you know, what do I mean by solvent? Okay, you know that a solvent is a liquid that's very good at dissolving things. Right? You put a piece of food in your mouth. You got the saliva of your mouth. The saliva has a large water content. What happens, right? The water of your saliva starts to penetrate the food you put in your mouth. It starts to get mushy. It starts to break down. It starts to dissolve a little bit. Water is very good at dissolving things, and that's an important characteristic to support life on the planet. You should be aware of this simple equation. Okay, a solution equals a solvent plus a solute. Okay, and so we already know what a solvent is. It's the liquid. The solute would be the solid material that is being dissolved. So let me give you an example here. Okay, let's say, let's assume you have a cup of unsweetened coffee. Let's assume you have a cup of unsweetened coffee. Let's ask and answer a couple questions here about this. Okay, so the first question in relation to the cup of coffee is this. What is the solution in our example here? What actually is the coffee? The coffee is the solution. Question two, what is the solvent? Well, it's the water, right? The water liquid component of the coffee is the solvent. Okay. And so question three, what is the solute? Well, the solute would be all the molecules, including all the pigments from the coffee grinds, the coffee beans that turn the water a dark brown or black to make the coffee when you brewed the coffee, right? So this would be the dissolved pigment molecules from the coffee beans that went into the water when you made the coffee. Okay. If you added a teaspoon of sugar to sweeten the coffee, well, the sugar would be an additional solute. Okay. if you added a teaspoon of sugar to sweeten the coffee, the sugar would also be a solute. Okay, folks, do you have any questions about solution, solvent, solute? Okay, so water is a very good solvent. It's very good at dissolving things, and that's important for the health of our bodies. Okay. All right. Thank you for the feedback, Shay. Appreciate that. Okay, let's continue here. Number 3, talking about important properties of water. Number 3, water is a very good temperature buffer. So I'll say it this way, water is a fantastic temperature buffer. Now be very careful because I know some of you have been reading your book and I love it. That's fantastic. I want you to do it. But when you hear that word buffer, new students tend to immediately think I'm talking about pH. I'm not talking about pH now. I'm going to talk about pH later. Right now, I'm talking about a temperature buffer, not a pH buffer. Okay? So remember that a buffer is anything that resists change. So what we're saying in this current context of the conversation is that water is very good at resisting changes in temperature. Okay, so here's an important question that we need an answer for. Okay. Why is it useful that our body is generally able to maintain a constant temperature? Because it is predominantly made of water. Why is it useful that our body is generally able to maintain a constant temperature? Because it is predominantly made of water. Can anybody want to try to answer that for us? Feel free to unmute your microphone. Feel free to type into the chat window. Why is it useful that our body is able to maintain a constant temperature since our body is made predominantly of water? Okay, so Shay, thank you for the feedback. You're not wrong. It's a, normal body processes can work correctly. So you're not wrong, but let me twist this a little bit. If your body did change temperature, why would things go bad? Why would things go bad? Okay. So Brittany, you're right. We want to keep a pretty constant blood temperature. That's true. And can anybody answer this?
I was thinking that it won't be affected by like the external environment as easily,
And why is that important, Raquel?
because like if we stepped outside, like if I'm inside and it's cold inside, and just because I step outside on a hot day, all my, like if our bodies were influenced by it a lot, like it'd be difficult to just change environments. Like we wouldn't be able to do that, but because water can maintain a temperature even when its external temperatures change, like that's how our like body regulates itself.
Okay, thanks, Raquel. You are not incorrect. You're not wrong. I'm just trying to probe a little deeper, and I see we're out of time. So let me give this to you, and then we'll sign off for today. Folks, if your body changes temperature, all the molecules in all the cells of your body, they will change their shape, because changes in temperature change the shape of molecules, and changes in the shape of a molecule changes the function of the molecule. How the molecule functions, what it does, how it works, how it behaves is changed by changes in temperature. So we don't want changes in temperature because we want our molecules to stay a constant shape so they do a constant job correctly. Okay. By avoiding temperature changes, the molecules that make up our body get to stay a constant shape to do a constant job. Okay? Think about it this way. Changes in temperature changes in temperature change the shape of molecules, which changes how the molecules function. Okay, think about it this way. Do you live in a house, or have you ever been visiting a house, maybe your grandparents, where a door in the house is harder or easier to open based on whether it's the winter time or the summertime? You ever have a sticky door? Typically in the summertime, the temperatures are hotter, so the wood of the door will swell a little bit, so it'll be tighter in the door frame and harder to open and close. But in the wintertime, typically the temperatures are cooler, so the wood compresses, and so it's the door is just a little bit smaller, so it opens and closes in the door frame easier. That's a very quick illustration of how temperature changes the shape of the wood of a door in a door frame. The same principle is true for your body. If your body experiences temperature fluctuations, changes, the molecules that make up your body change their shape, and they do not function in a proper manner anymore. This is why you feel horrible when you get a fever. That's why you feel horrible when you get a fever, because the change in temperature of your body is changing the shape of molecules so that your molecules don't function correctly, your body is not functioning correctly, and you feel ill in response to that. Okay, folks, I'm out of time, so I'm going to stop here. But I'll just ask you, is there anything you'd like to ask a question about? Okay, I hope you're not passed out on the floor somewhere. I hope you're doing okay. So have a good afternoon, a good day. We'll see you on Wednesday, big day Wednesday with lab and everything. So take care, folks.
Have a good
Thank
day.
you.
Have a good one.
Bye-bye.